All right, so last time we looked at this. We spun that thing around in the circle, and we saw that the ball came out in what direction? What letter? B. Comes straight out. Unless we have the weighted ball, which I still like that idea. I think that'd be interesting. All right, what other things did we learn? Give me an equation. Marshall, poof me an equation that we learned last time. Any one of them. There was a lot of them. Any one of them. Any one of them.
Velocity equals 2 pi r over d.
I like that. So we had a velocity equation. 2 pi r over t. All right, so we can also say that t is equal to 2 pi r over v. All right, give me another one. All right, Max, you're up. Okay. Hold on. Give me something that involves Greek. I don't remember the letter, but it's a little weird W equals weird W. Omega. Omega equals changing theta over changing time.
Change theta over change time.
All right, so we started down this path of all sorts of weird Greek symbols. Now, what did all this stuff mean? First, we need a circle. Let's pick the color circle. We got green, red, and yellow. Anybody have a strong opinion on the color of the circle? Yellow. Yellow. Opinion has been chosen. Here we go. Ta-da. That should be enough of a circle for us. All right. Now, Matt, since you opened your mouth. Velocity. How do I draw the velocity on this? What kind of velocity would it be? If we're going around the circle in uniform circular motion.
Tangent.
Tangential velocity. Which way do we want to go? Clockwise, counterclockwise? You're still in charge.
Counterclockwise.
Counterclockwise. All right. So we've got some sort of velocity that's going like this. All right, and we can call that the tangential velocity or the linear velocity. Either one works for us. Eric, now I'm going to put omega on this. What does omega refer to on this circle? In words, what is omega?
The radian, oh, not radians.
You're not wrong with radians. It's the change in radians per time. But if I call this the linear velocity, what do I call this?
The tangential velocity.
No, not quite. Anything that is Greek is always going to have the same word in front of it, which is what? Thank you. Travis got angular. So we're going to angular velocity, angular position, angular acceleration. We're just going to keep tossing that word out in front of everything. So this is our angular velocity, which refers to how fast we're going around here, omega. Now, Patrick, what can you tell me about omega? Is it changing? Is it constant?
Constant.
It's constant as of right now. We said uniform circular motion, that we're always assuming that omega is constant. So this is some constant rate of angles that we're going through. Awesome. Now, I also introduced something else. What was the other term that we introduced? Shui. Frequency. We did do frequency. That's not what I wanted, but it saves you from answering anything else. Good choice. Adam, if we did position, velocity, what's the next thing I'm looking for? Acceleration, of course. And we came up with some sort of acceleration term. What did we say that acceleration term is equal to? Remember? Yeah, we said omega squared r, or there was another way that we put this too. Thank you, Matt. V squared over r. And Matt, where did we get this equation from? We poofed it out of thin air. And I promised you that today we would go through where it came from, and that's what we're going to do. So today's topic, or at least the beginning of today's topic, is the centripetal acceleration. Where do I draw this acceleration on this diagram in the first place? Connor, any ideas?
Just
the general
Yep.
toward the center?
Always towards the center. So we always show this diagram, and we draw this acceleration. We say wherever we're at, we've got some sort of acceleration that is pulling us towards the center of the circle. And we learned that you need that velocity to keep you in uniform circular motion. So if I have my monkey of science here, and I'm spinning my monkey of science, the only reason he keeps going in the circle is because there's some sort of some sort of tension in the string that is holding him towards the center of the circle. The second I was to cut the string, off goes the monkey of science in whatever straight direction he was moving last. All right, so that's the direction of our acceleration. Now, where in the world did that equation come from? I'm going to show you two ways to find this equation. One you're not going to like, because it's going to involve calculus. But that's the way to show it. So we're going to do the mathematical way, and then I'm going to show you the nice Dr. Seuss way of hand waving and triangles. So that'll be easy. So let's start off with the first way. All right, what we're going to do is we're going to add a coordinate system to this guy here. All right, so we'll call this my x and my y coordinate system on this circle. And I'm going to say, for example, that I start at some position here. And I'm going to draw in my position vector. We'll draw it in red. Shane, pick me a letter to represent this position vector. Any letter.
Z.
Z. Wow. Is that right? It was the same one that was chosen before by the calc-based class when I did this. I remember that because the whole derivation was with Z. All right. It has been chosen. We will now write Z in our notes for the next 15 minutes. Okay, now I need to represent this vector in terms of components. Does that make sense? All right. So I'm going to have a zx component here, a zx vector, and a zy vector. Okay. Now, I'm also going to define an angle here, theta. I can write that position vector, z, as z cosine of theta as a function of t, multiplied by a hat, plus something we're going to call z sine theta as a function of t, j hat. Now, what in the world are these I hat and j hats? You guys haven't seen these before, have you?
Sure haven't.
Yeah, okay. You don't have to worry about them other than for this next 10 minutes. What they refer to is in the x direction here, here's my I hat vector, and here's my j hat vector. They're vectors that move in the x and the y direction and have exact length of 1. And it allows me to reconstruct a vector by multiplying a magnitude times a unit vector of length 1 in the y direction, or in the x direction, multiplied by a magnitude in the y direction multiplied by a y vector. Just pretend it, not your head. Good. I'm reconstructing a vector. Basically what I'm saying is the vector zx plus zy. I can say that this whole thing right here is my zx, and this whole thing here is my zy. Okay, we're going to add those together. Now who has had calculus in here? Okay, a few of you. Now I want to go to velocity. How do I go from position to velocity? Thank you, the derivative, that nasty word that we don't normally say in here. And then how do I get to acceleration? Derivative of the velocity. That's the whole point. So we take this ugly thing and then make it uglier once and then make it even uglier again until we get to the acceleration. Follow along, kids, it'll be fun. All right. Velocity is going to be equal to dz over dt. By definition, the velocity is the time derivative of the position vector. Now, what you guys are used to seeing this as delta z in this case over delta t. But that's fine. We're going to do this in the calculus, which is the derivative. Now, in that, I've got to take the derivative of this thing. Now, if I look at this, I have to take the time derivative, so I have to look at things that change with respect to time. Patrick, no, actually, I already picked on everybody but Dakota in the front row. Guess whose turn it is? All right, Dakota. The magnitude of the z vector, is that a function of time or isn't that? Is not. And what do we even mean by is that a function of time? Can somebody translate that to English? Perfect. As time changes, does z change? If someone asks you if something is a function of something else, that means like if x is a function of y, as y changes, does x change? That's all that means. It's fancy speak for that. But in this case, if I say is z a function of time, you say no, because the magnitude of z is always going to be the same as we go around this whole circle. The vector z, on the other hand, not the same. It changes. It changes because the direction changes. Okay, so it's a different vector because it has a different direction. Every vector has to have a magnitude and direction. Okay, so when I'm looking at this, what part of this equation changes as a function of time then? Theta, the angle. It's the angle that we have to worry ourselves with. Okay, so when I take this derivative, I don't even have to measure, I'll mess with the z up front, but then I do have to take the derivative of cosine. Now, if you guys haven't seen this before, the derivative of cosine is negative sine. So that becomes negative sine of theta of t. And the problem is I also have to take the derivative of theta of t. So I end up with d theta dt. Now, I have to do the same thing to the second part. So I get plus z times the cosine of theta of t times dt. Whoops, no, lies. Times d theta dt. And this is in my j hat direction, and this is still in my I hat direction. The first part is in my I coordinate, and my second part is in my y coordinate. Well, that's ugly.